All right, and then
The only thing I can do at this point is mess up.
okay, you might want to go to the channel and see if the stream out is okay. It's working fine. I'm gonna get you a microphone straight.
You guys come for the event? Yes. Oh, nice. Justin.
Oh, you're just me.
Yeah, Justin.
Yeah.
Yeah, you meet me.
Nice to meet
Yeah, cheers. Yeah, so this one, most of the presentation comes in Intel Labs. And I'm not specifically in the lab, but I work with our radius group. And we're starting to take some of the technology.
Test. Okay.
So, but I think the neuromorphic part is kind of more academic, interesting side of presentations. So I figured I'd start with that first. So it didn't seem so.
Okay.
Yeah. Like a whiteboard?
A board. I'm Star Trek.
Oh, board. Yeah, no. You know, actually, I'm planning on doing some hands-on demos. Yeah, but you know, our IT department is like really overzealous. So I'm putting all these instances. Yeah. So I know. I've deployed all these instances in AWS, and I went to use them, and like I was pulling my hair out because I could not figure out why I could not like SSH in them, and then I realized that they'd set up an automated script every time I would add firewall rules. It would just delete one of my firewall rules. Yeah. So I'll have to. The next time I do this, I'll give myself a little more lead time to figure out how to work around that. I'll be involved VPN or sometime, but yeah, it's yeah, no, it wasn't meant to go like that. So it'll be all slides today. Yeah. Okay. Yeah. Are you guys familiar with Keras? It's kind of like I think Francois Chalet's Euro API that goes on top of it. Deep learning framework. So you can take a Keras model and you can turn it into a script. And I was going to show you, but I'll probably just maybe flash it just so like folks can see like what it is. It's actually part of the framework that we're not even involved in. At least if you want to play this. What are you guys doing? Any kind of like machine learning scale or robotics or? Fair enough.
Yeah. Come with some projects.
Gotcha.
Data. Data build a database. Oh, recognition patterns. Yeah. So that
Yeah.
we can actually.
Oh, interesting. Yeah. Did that stop with an aquarium?
Just before. I knew it was going to happen. I was going to do this.
Yeah.
But it's true. A couple of months that happened. Showing it on the product numbers.
Yeah.
But the data they got from was actually in the labs.
Okay.
So
So
we're
we
going to
use.
use, yeah, we're going to use it on. And the soul
Test.
It's so like release it. I'm like.
They were too much of that. It's almost like having someone at maximum security. Dozens of people.
Yeah. I was gonna say like some shark videos, you know.
Yeah.
Or probably kill her all.
Maybe they could.
Yeah, I think an orca would eat it.
Yeah, so yeah, putting it on speaker more.
Let me know.
That's the kind of data I was taking.
So were you guys like, were you working with like a biology outfit or what?
Yeah, it was the, at that time, it was the, she was the.
Is it better now?
Lead researchers that brought that specifically.
Yeah.
Spent most of the time actually.
Okay.
She went back.
Oh, cool.
So she happened to have this.
Yeah. So were you doing that through photographs or were you doing it through audio?
So
Let's do this. Yeah. So I guess, did you have a setup kind of similar to FaceTime where you run the audio through a recurring network, kind of like embeddings, and then you can classify like the
that sounds too technical for me.
Okay.
But I think the idea was to, yeah,
Yeah.
So it really, it was had to do with what they were reporting at the time, which was usually the goal.
Right.
So, sure. It actually stemmed from another idea that I was looking at. Sounds, frequencies, public safety.
Straight as running.
So if I break this way, then compared to regular glass.
Like specific
Yeah.
allows you to figure out, okay, it was ambition. That's
Yeah.
so like a gun shot.
Yeah, it's like, I know like certain alarm systems have like glass breaking sensors and they respond to specific frequencies.
Yeah.
Your Wi-Fi blocking for being fine.
No, I should know about you.
Yeah.
Yeah, you just work it. Fine.
I remember there was, or maybe it's a different product, because I remember at one point I was reading a bunch of, I think there were other companies doing this too, but they wanted to listen and then deploy the software based on where, yeah.
Great.
I didn't get that.
like a microphone anyway.
I guess Detroit would be a good place to make that.
Yes.
Yeah, the original one was called Shot Spotter. This was like about 15 years ago. And that was around the time. And so they actually had it on top of civilians. And the reason is because a lot of these people call the police. So the police were already there by the time they did fly. So that's more of my area.
Oh.
So the shorter the time gap between the incident and response, yeah, the more likely it seems. No, right. Yeah, that was kind of interesting. I think I would think I was actually prime instructor.
Really?
Okay. When it was rolling out.
Yeah.
And they were CP for the rest of the province.
So
Well, you know, right?
yeah,
Wow.
back in 2012, 2013, I just got out of university and we had started, and we wanted to improve all the UIs and some of the databases on Prime. Because, you know, at that time, it was like awesome. So we had a champion in E Division who was kind of, you know, pushing us forward, and we, you know, starting to get a little headway, but the problem I'm running into is like crime is legislated. And it was just really unclear, like, who you sell to. It seemed to require legislation to like anything that was significant. So we ended up creating this dispatch system and deployed it at this nonprofit called Convergence. And it was kind of cool because we put iPads on the cars, we made everything touch friendly. And we even built up a dispatch center, so they had this like big image, flat screen, and they could see where all the cars were, and they could route them. And we had a whole drag and drop dispatch system too, so that way they could like visually allocate all the resources. It was ahead of its time, I think.
It's great.
Yeah. So yeah, it was
layers
definitely.
of layers of stuff to get.
That's right. Yeah, it was challenging. So, anyway, it was. I personally would like to resurrect not on the police side, just on the dispatch side, because I think now like, there's a lot of volunteers out there who are well trained, and like this whole. I think there's a bit of a shortage just in terms of like medical personnel. I think you can just route all the volunteers and volunteer firefighters and just like, create something like a Uber and just dispatch them around the city bruises and scrapes, broken bones. Yeah, exactly. Yeah. So I'm gonna apply to be the volunteer firefighter in September.
They have a.
Yeah.
Yeah. They have regular.
So that department gets a volunteer,
That's great.
and it's a really low call volume. Like it's only, I think it's either 12 a month or a year, right? It's really low. So I was like, well, I work from home. I mean, my boss says after 2 o'clock I can do whatever. So I might try to take it on.
Because I'm wondering, because
The calls, the call volume,
yeah.
the volunteers. It's
So just
unfortunately-
volunteers is for
Yeah.
strictly fire, but non.
I think they do some medical, but they're all trained, they're all like level 3 trained. So, I mean, you could probably slap on a little extra to get training.
Sure.
And, you can utilize it a little more. Because it's a really quiet department.
And it's still close enough. It's pretty well known.
Yeah.
Do you guys do you know if the department gets called to other cities?
I have no idea. I did chat with them, but we didn't get that deep into it. I figured like my goal was to just kind of get trained and learn the basics first, and then dive into deeper.
I just didn't have to.
Yeah.
Have something like that. Not just for fire.
So
There's
I know, yeah.
auxiliary policing.
Yep.
I was.
Oh, you were okay.
That's what it was. I work civilian. So there's always opportunities.
That makes total sense. Because
This is great. I'm so glad I came.
yeah.
Someone who actually.
Yeah, no, that makes total sense. Well, it's funny. So, the reason you're going to get picked out of this, the reason why I got thumbs up from my boss to like, hey, we'll apply to be a volunteer firefighter is he used to be a volunteer sheriff deputy in Arkansas.
Oh, wow.
Like, literally, he said, they just give a holster and a gun in the back, and he get in his car, and he drive around Arkansas, county in Arkansas.
Tickets and stuff.
I didn't get the details. I really want to ask him now. I have a feeling it was just like taking reports and stuff like that. Yeah, exactly.
You get pulled into stuff. I get into stuff. It's just like, really, I can remember struggling with a guy double my size. Yeah, it's slapping this. It's the adrenaline's back, and they're struggling.
But if you're, I assume that you're really RCP, probably a little better outfitted than just like.
No, they probably had guns. We had
Yeah.
guns before. First nothing, and then they had guns for. Outfit had been removed. The guns went to the sheriffs.
Yeah.
But we had everything else.
Did you ever go full screen?
Oh, yeah.
Were you using your personal vehicle?
No.
Okay, so
Yes.
you were driving.
Yeah, that was kind of fun, right? So
Yeah.
we're not supposed to.
Yeah.
The odd time we did train on instead of seeing one reader cards, public system.
Yeah.
Or usually most of the time it's actually with a passenger. So I'm the one at that time they had NWS, the full prime system. And then I became a prime instructor, so it was cool because I was paid as an instructor, right? For the university, Chilliwack.
Yeah.
Right. And then at the same time, I was auxiliary. So I would do prime training for daytime and nighttime. Put on my cape and get in the car with them. So it was great with the guys because some of the places were rolling out there just new for prime because it was just Richmond. And so get in the car and I would just system. So it was like an extra eye for them. So
Yeah.
they liked it because they could just drive. So it was all a lot of fun back then. I know you know it's kind of like this kind of show.
I didn't follow it. That
That
close.
was like 2 years ago.
Really? Was that because of the pandemic or was that because of the?
There were a couple of incidents where it just got too risky. I thought the program was risky.
I can understand.
And I could see that. So,
Yeah.
so I get it. So the fun while lasted a while. We got to do some fun stuff.
Yeah, of course.
But yeah, my background in crib, I always looked at stats. Okay?
Yeah.
So I really looked at this sort of thing for part of safety. So the time between incidents and response. So everyone saw potential. So what you're saying, yeah, actually, that's great. To have people that can still be deployed for minor things. The only liability thing I can see where I can say is that there's a liability issue in case something where this always usually happens. When an incident happened,
Yeah.
something happened, my neighbor's spraying go there, there's a neighbor who takes out a shotgun. Really escalates. It's not quite described as
Yeah.
the case.
Yeah,
But I still think it's a great idea. I think it's worth
I think, well, I think police would be a little hard, police would be, I think, much harder, but I think it should be focused on really low priority, something that, first aid level two. And handle that sort of thing. Because I've taken stuff once on the sidewalk and split my face open. I'd be able to start from here. And it was definitely a hard fall. And, like, fire department just said, just kind of bandaged me up. I said, all right, go to the ER. I mean, it was just kind of nice because, at least I got to look back because we didn't want to lose me in case of concussion. But I was thinking, oh wow, like there's probably a lot of stuff like that that's just not critical. That's like, if you have volunteer force. There's something like it in New Jersey City.
That's what I love about America. They're the ones that have walls and strikes.
Yeah.
They're like, okay, we'll give it a shot. Here, it's like, we gotta go. I think it's a great idea. Like here, houses, heat don't have.
Yeah.
It seems to be the trend. And you have this units. It's dispatched for stuff.
there.
Yeah.
Yeah. We kind of like the cancer parsers. I mean, cancer parsers, I don't know if they're still operating. Their funding is like up and down. I think it's been on for several years and it's on again. But it's a partnership with the Canadian Cancer Society. And what they do is,
I guess
there's people who want to know the science.
Oh, good. Yeah.
You know, so how does the, you know, and the rule is they have to be able to get the car on their own. And if they get the car on their own, either right or the other, you know.
I don't know data scientist.
Low hanging fruit, but okay.
I'll just do a little piece. There's a group called Synchronous.
Yeah, I've heard of it.
You know, Catholic stuff. That is wrong.
Not very well, but
At the end of the day,
it is.
we each get a 20 little.
Yeah.
So this could work. We're going to get volunteers. Consensus. That's what you ask.
That is the most.
Yeah, tell you what, I'll grab your contact info.
Sure.
And I'll just send you
Yeah,
a
so you-
quick message here.
Finally. Yeah, I guess so. Maybe he'll describe what he does. Right? So, if you want to introduce yourself.
Sure.
What's the public cloud technology?
Oh, so it's really just a BS title. Yeah, so I work with a data center group at Intel, and it's really more of a sales focused role. But the thing is, I don't just do sales, I do more than sales. I do a lot of developer relations, and outside of that, I come from a software development background. So, you know, for me, it's not like I don't have a sales role, but I work with a lot of sales, and then I work with a lot of researchers. So I mean, we were just trying to figure out what's something that can capture all of that. But all the accounts that I work with, they're all big companies on the cloud, with the exception of a couple of them that are data center. Yeah.
Intel thing.
Oh, well, what do you mean, Intel the company, or?
Well, the cloud, the section we're working on.
Oh, okay, got it. We actually sell the hardware to the cloud. So yeah, so they're buying our CPUs and chips. Yeah. So yeah, I've actually got. I have a whole other presentation I'm doing on Java on the 2nd, and maybe I'll send that out. I don't know if there's any Java developers. But yeah, but it's really about how you can choose the right instances in the cloud that's going to give you the best performance in Java. Because I mean, really, in all the CPUs that we make, every generation has new accelerators, and there's always AVX 512 stuff in there that's speeding up all of your software. So it's if you're doing math and Java, choosing the right CPU and the right JDK is gonna make it 2 times faster. Yeah. So that's a really more what my job's about, is helping people optimize all their stuff. Because you'll find that companies are they'll just choose the cheapest instance on Amazon. Without real yeah.
If you want something bigger.
Exactly.
You don't really know how.
That's right. But that knowledge of oh, wait a minute, why should I use an M6i versus an M4i? It hasn't really proliferated, so that's why I'm doing a lot of developer relations. It's just educating people on that, because I mean, you'd be surprised the amount of money you'd save.
Are you talking about things like that today?
No, this is all about like machine learning hardware and a little bit about SNN. Yeah. So yeah, that's not exciting. Yeah, I mean it's a data science machine learning meetup. So
What's SNN?
spiking neural networks.
All right.
Yeah.
They are developing some like specific hardware that like Google has this thing they develop like
Oh, the ASICs, the TPUs.
TPUs, yeah.
Yeah. So we have stuff like that. You're gonna learn about that. Yeah.
Mostly like focused on FPGAs and ASICs for optimizing.
Yeah, like Intel, like NVIDIA is really good, I think, in like pioneering. We're about like scale and lowering the costs of things. So, I don't want to give a presentation, but you'll see how you'll see how we do that.
So I'll just give you a brief introduction, and then when you start the presentation, you can
Yeah.
give whatever additional information.
Yeah, absolutely. Yeah, absolutely. So, yeah, my real job title on paper, which we never use, is industry technical specialist. But it just doesn't. It really doesn't speak to what I do. It's very vague.
You have to try different things to see which one sticks.
Well, what we're actually going with, so that we are internally, we're working on changing all of our job titles. So I think next year, based on a vote that just happened a couple weeks ago, I'll probably be called something like a cloud solution architect. So, which I think is a lot more accurate to what we're doing. No, I live here. Yeah, there's actually 200 people at Intel that live in Vancouver. And all of them are office here in Marine Drive. Yeah, but it's very empty. We used to have one on Broadway. So there was one on Broadway, this is before my time. And that one closed, I think, 5 years ago. And they just started getting people working remotely. And they just kept 2 floors in Marine Drive. And it's really just there to have like an office, I think. So, there are some teams that have to like be there 24/7, but not me. I work with the US team. So I would say 3/4 of like the companies I focus on are all Bay Area based. So it's funny. So people don't know this. We actually have our own private jets for the employees, like not just the CEO, but for the employees. So we have these like, I think they're Embrace, kind of like those commuter jets you might take in Kelowna or something. So we have 6 of them, and we have to all the major Intel campuses from like Portland to San Jose to Folsom to Arizona. Our jets fly to each one, and they're always going. So you can just book a seat; it's free. If you're an employee, you can't take anybody else with you. But if you're an employee, it's free. And yeah, and then you can just like fly people back and forth, which is kind of cool. So
personal or this?
yeah. So, but we have a lot of folks going back and forth from like campus to campus. So a lot of times we'll do like an event. We have like 3 campuses, well actually 4, but 3 major campuses in Portland and out in Hillsborough. And it's funny because the biggest one, Jones Farm, literally right next door to the airport. Like you could walk across the street into the airport. We have our own terminal, and you just walk on the jet. It's pretty crazy. Like I've never seen a company do this before. Like the logistics, I've just never seen anything like this before. So yeah, Google has buses, Intel has jets.
So is Intel worried about the carbon impact of
So besides the jets, I think they're using offsets for jets, but 100% of our energy in North America, Europe, in South America, and all of our main campuses are renewable. So it's all green energy. And you'll even see like we got a new campus in Arizona. All the parking lots are covered in solar panels. So we just generate our electricity. I actually just got to do a tour of our data center in Hillsboro. I think it's JF3. And right next to it, we have like the entire parking is covered in solar as well. But all that energy is purchased through renewable credits as well. So, because in Eastern Oregon, there's a bunch of solar, wind, and then you've got all hydro from Columbia. So you basically get direct renewables from there. And the way that you do it is, you come up with purchasing agreements with utilities. And then essentially when you hook into the grid, they allocate the electrons to your data center, and then it's all 100% renewable energy. But it was a pretty interesting tour. They actually divulged something which I've never heard of happening in the data center, but so this one had redundant cooling, but one of the chillers went offline, and then another chiller also went offline like a couple days later while they were repairing the other one. And they tried to do a shutdown of the data center, but all the machines shut down. Inside, the internal temperature went up to 170 degrees. And then in the contained rooms where the racks are, they think it went higher than 200 degrees. So, you know those like emergency exit signs that are above like each door? They melted. They literally just melted. They had to replace them all. So it like shows you like how much heat like a data center generates. Yeah, it was a pretty remarkable thing the way they're describing it. So I'm sure that's happened in like other data centers and stuff. I personally, you'll never hear it publicly, but it was interesting. Like they didn't have to call the fire department or anything. It was really just like phone text and turn the chillers back on. That's really all.
But there should be fail safes for temperature sensors that turn things on.
Yeah, well, the problem I think happened was, so when you deploy like a server like that in a data center, it's supposed to have configurations to tie into like the rest of the infrastructure. And I think the issue was some of them received the incorrect configuration. So when failsafe went out, when the kill signal went out to all the servers, it just never shut down. So the servers just kept running, and a lot of them were running at full capacity, right? So, CPU is running at 100%, but that data center is used for kind of like simulation and stuff. Yeah, you're just outputting heat, more and more heat until finally it just melted stuff. So it's a.
Was the data center working after? Was it only the sides that melted?
Yeah,
they were stuck.
So I can't. Yeah. So the signs. Yeah, the signs they replaced, and some of the machines they had to swap out and get rid of. But yeah, I mean, pretty much the way that data centers are designed in general, like everything, like all the machinery is somewhat expendable. It all has a shelf life. So, basically everything gets run until it breaks, and it's just the cost of doing business. So, I think for a typical data center, when an incident like that happens, like all that stuff will have been in there for probably 5 years at least until it fails. So it's like, okay, well, it's in the budget, just replace it, whatever. Yeah.
I did my master's in electrical, so being inside data centers.
Yeah.
So I was focused on VLSI. So I'm pretty familiar with that.
Okay. Cool. Which data set, like bigger data centers have you been inside? Like were you?
So I did my master's in University of Hong Kong.
Okay.
Now I'm on fabrication 100%.
Got it. Cool.
And
And I guess the data center was probably used for like kind of chip simulations and stuff. Like, yeah.
We also had a data center in my previous company. Like they have their own like telecommunications network all over the country. So we have like 5G servers inside the data center.
Wow.
I've been inside the data center.
It's a fun tour. Like it's crazy how, like air filters, the way that they scale up air filters. It's just kind of like next, blows your mind how it all works, and then the amount of electricity and all the transformers and everything. It's really interesting to me, at least. So, yeah.
Huge fridge.
What's that?
It's a huge fridge.
Yeah, it is. You're absolutely right. It is. It's just a massive fridge. That's really what it is. And you'll see like massive cooling pipes too. Just carrying chilled water and hot water back and forth. So I assume that you moved to Vancouver and you're working for an outfit here?
Yeah, we work for theory and practice. We're a data science consulting startup.
Okay, cool. And what kind of like problems are you focused on? Like, are you just focused on like mostly working with current networks,
We
like
work
anti-fraud?
on retail and finance.
Okay. So give me an example of like a problem that you've been focused on for retail.
So we just went live with a recommendation engine for a client in the UK.
Nice.
So they have like their own kiosks inside they have like 600 stores over the UK.
Yeah.
And inside the stores they have kiosks where people can self-serve. When they place orders, like we show recommendations. They can select like whichever one they want to add into the bag. So we went live with that. We've also done like demand prediction and supply chain optimization for retail clients.
Yeah, I think recommenders are a big one right now, especially in e-commerce. How did you handle like the EU regulations?
We host everything in EU. So
Yeah.
we have our infrastructure on AWS. So like when you like host everything in EU,
Yeah.
it complies with all the GDPR regulations.
Cool. And then for the recommendations, because I think at one point didn't the EU come out with a specific regulation that was like, if you recommend something that the customer didn't actually need, like you were liable for the cost of that, or I can't remember exactly how it worked, but did they end up making that? Okay, I guess they didn't ratify that. It was a pretty crazy regulation. Like it was like a very, I remember when they came out with it, I think it was about 6 years ago, and I was working for a deep learning company at the time. And we were looking at doing like e-commerce with a German tool company. And they were just like, we're so scared because like, what if we recommend the wrong tool? Then like, they can come after us, Like
It's a technical recommendation or general like on like Amazon and people scroll
and Amazon. So basically, like if you were on a web page and like on Amazon below their main listings, it says like, if you buy a toilet, maybe you should buy toilet paper with that toilet, right? So let's say Amazon recommends plunger, but the customer really didn't need that plunger. Then like the regulations said that they were liable for that plunger, like cost of that plunger, and they can take that money from their revenue. It was a yeah, I don't think it was ratified. It was a wild piece of regulation. I think like at that time the EU was like really scared of Amazon, like just in general.
People
Like,
can choose, right?
yeah.
Even devil is not responsible for the temptations. Like, you want to take it.
Yeah. So anyway, yeah, that was a pretty fun trip. I would have to say. It was like we were doing my favorite one when I'm working at that company. We did a big anti-fraud project, and it was for one of the big telcos in France. And it was crazy because they had a subsidiary in Africa, and just the things that people would do to bypass billing systems would blow your mind. So there's these things called SIM boxes you can get. And you can take the SIM card, like, ordinary SIM cards, put them in SIM boxes. So basically you're simulating like 100 cell phones with 100 SIM cards. And what these guys would do is they would hook them up to the internet and then just do kind of VoIP calls. And they'd sell calling cards of like mobile phones and stuff. And what they got out of it was they were able to bypass the billing system, like the international calling billing system.
Kind of like magic words.
Yeah, and then if somebody's calling somebody in Uganda or whatever, they have a SIM box there and it would terminate the calls in Uganda, and all the audio would be carried over VoIP. And so they just make a killing because they wouldn't have to pay the carrier any extra fees; they're just getting charged for the costs. But they hand out little calling cards, and then of course they can charge it if they want with those. And then when they figured this out, what they would do is they would take the SIM boxes and they put them in vans, and they would drive the vans around town. Like the people who love committing fraud will always find a way. It's so interesting. And it was just like, it was kind of like that whack-a-mole game. And so we used kind of LSTMs to try to do some anomaly detection to find these guys. And some of it was deployed in production. I think there were a couple of things we did where it was deployed in production. But I mean, the reality was you deploy something like that in production, it lasts at most 6 months. And then they'll find a way around it. Yeah. So, yeah, it's just.
You increase the cost for them. So
yeah.
it's not really hard.
Yeah.
They will find a way.
So it's the four of you who are cool. Yeah.
Just so everyone's aware of what's going on, we'll start the talk at 6:30 sharp. So it's normal in these kind of meetups. Start the talk at 6:30. Everything before 6:30 is just unstructured networking, socializing. So everything's still going according to plan. We're not making it. Also, I'll point out we're currently live streaming everything, so don't exchange sensitive personal information. It's all going out to the public.
Is it live streaming right now?
I think so.
A couple things
I don't know how to work it, so I'm just letting it.
Well, that was like 6 years ago. So
I'll ask you later.
Yeah, no, I think the NDA has expired on that one. So I think I'm probably safe on that. Yeah. Sorry, Absolutely. So UBC has a really interesting ethics. I think it's a whole ethics program in AI and robotics, and absolutely you have to know, because where it gets really sensitive is financial data, like say credit data or something. Because if you're a bank and you're trying to qualify someone for a loan and you've created a model to qualify that person.
Yeah, I just,
there's so many things that
I was
go on. And the problem is, if the data, like, listen how you prepare your data set, you could easily discriminate against somebody. Like very easily, just based on like, if you're using names as features or zip codes as features, stuff like that. You could very easily discriminate against somebody. So, because like denying somebody a loan, sometimes that loan is what leads to them like just becoming more economically viable, right? So.
But in general, banks have been able to
challenge is hybrid
develop
models.
a learning model. You layer how to prove that's what you use, how you train it, and
Yeah.
what it has in general, data scientists I mean, you need to be aware, but in general, you always have to go through that department.
Yeah.
So I think
So,
those
yeah,
proposals, have you participated?
Yeah,
absolutely. Yeah, so, good.
But honestly, you know, where it even gets trickier is, you know, this is kind of like the dark area.
That was like my favorite.
Is you can, like,
Well,
let's say you're not
they
allowed to use
naturally
certain pieces of data because of regulatory purposes.
Just because a little bit of latency, they kind of
You
jump
develop
in.
proxies. So you can figure out proxies, so it's on the zip code. You look for street names in that zip code, like there's different ways you can develop proxies,
Ideas, like,
you know, get around that.
kind of like choose separate groups.
And I think that's just why, like, you probably want to be familiar with that. Let's say you develop a proxy,
Or just doing their own
well,
separate
if you
structures.
develop a proxy, is your proxy still, you know, even though it's allowed, is it still ethical? Is it going to make the world a better place to put it? So, yeah, I think, but you're 100% right, like it's the departments and things are pretty crazy. Yeah. So, I know that UBC has like a big program, a friend of mine, actually, so look her up, her name is Adjunct Moon. She did a whole, I think she did a PhD. Is that a PhD or law degree or some kind of, it was a pretty big program. But it was in like AI ethics. And she even at one point was like consulting with the UN and stuff because it was so important on like why everybody had to be familiar with all this, because there are a lot of ethical implications. I think it comes down to, definitely comes down to like, as I said, I'm pretty sure there's different like smaller courses you can do. So my suggestion is look up her name and go and look at her like past work, because you can probably find like smaller courses or just information or just self-educate yourself on it. What's that? Adjunct Moon. So AJUNG, Moon like as in, but also. Yeah.
Most likely you read the paper. So I think that also helps. Again, people who just show up.
Yep.
I don't want to discourage it, but it's just like you will get.
If I go online, 3-year-old and a 7-year-old running around, I'm not putting it anyway.
Well, they get
So-
cats and.
So I assume you're doing data science, right? And like, so what part of the do you focus on?
Yeah, afterward was
Yeah.
I've been doing that today.
We have a reservation in that.
I was thinking like, that's. Yeah.
Yeah. Interesting. Oh, sorry. Oh, I thought you were saying that's.
你去錯標頂㗎，
No.
即係嗰個買隻翻過嚟咧，就算都係新標定係咁靚㗎。如果你
Yeah.
新標定係好靚㗎 ，brand new 㗎，brand new 㗎，好靚㗎，搭嘅時候好靚㗎，好似係14樓，你當啲佢哋嗰時。
But people kind of have purpose anyway.
Last time I checked with him,
Yeah, within 17 or 18.
So let's go to this one. So this is the one first step
So, okay, so when it comes to privacy and security, I think where you're gonna find more that's more relevant is probably, I think the ethics side the data scientist needs to know. But the privacy and security, that's really for DevOps, you'll find that like DevOps practitioners, engineers, they're turning into DevSecOps. So companies, like let's say accounting software company, DevOps become DevSecOps because they're the ones who are controlling deployment, they're the ones who are doing a lot of network configuration and everything. And through that kind of continuous deployment kind of culture, you want to add security in there. So for in your scenario, like so you're doing data science, you're going to focus on the ethics of like what are your data inputs, but when the model's trained and you have to deploy it in production, privacy and security is really going to be up to like DevSecOps. I mean, there's a little bit of privacy in the data that you're using too, but I think more, it's really more for deployment problems, at least the way that I'm looking at it. Yeah.
They do have other spaces. If you go over there,
Yeah. So you look embedded on T. Okay. You don't work at Microsoft, do you? Okay, because that's like a Microsoft model of doing things. That they actually came up. Microsoft was the one that like developed that like the model of embedding data scientists into teams. Yeah, which is the only reason why I asked.
Because you know it's stronger or
it has to align with their interests. So you probably could have like a
Yeah.
tier checking. Because we're bringing in people from like the tech industry and inviting their students in and doing it as well. It's like an interesting opportunity.
Exactly, I think that's our motion point is we open this up. I think every university will jump on this. Not caveat because that no longer does, but I think there's a lot of just colleges.
Yeah.
Who would really real kind of there.
Yeah, because they want to have connections.
Past the hour, is that the conversation ends?
So is it? Yeah, I can. Yes, hi. Hi. Yeah, nice to meet you. Good.
Everyone has to come a first time.
Yeah.
It's not that.
Similarly, most people's first time.
Yeah. It's kind of a reason. Not too actually. I've been by the wayside till we don't
We haven't.
Oh, yeah, the word.
I know. It doesn't.
Yeah, I know. Scheduled until 8.
It doesn't fit with my
I'm gonna try to get this down.
schedule.
Yeah, so that's an hour and a half. I think it's kind of.
I think a lot of us have Zoom fatigue. You know, we've done a lot of online meetings and stuff. I don't want that's another Zoom meeting.
Yeah, I know some more Zoom meetups. Then I guess.
Yeah, I mean, once you start talking, you're going to open up the stream and try to keep an eye on that.
But it actually could have been a good idea. Since the first person around for a couple of years,
Yeah.
especially if you're expecting a lot of interest.
Yeah, that's another thing with organize. Yes, no, I know. And then it's like a budget thing. Like you need to pay.
just say it right now.
Yeah, so let's bring a name tag or you're not allowed.
Yeah, that's right.
Oh.
No.
Yeah, my attitude is.
Yeah, no, I get it. I'm happy to help. Yeah, I know why. So maybe.
That was like little
So you're with an agency now?
More or less.
Okay.
Yeah.
Well, I don't need. Oh, I don't need create graphs.
Just see in person.
Finally, I see already.
Yeah.
We're going to.
I can tell you what else.
Let's say, find an edge, and you change it. So you have to recommend your, let me say, what's the likely are actually associated with the customer. You create graphs and show.
They had prime.
So on. Yeah.
Yeah. Yeah, I think like a lot of pages. See, a lot of this stuff has to do around that. I help you. So, I should see that. You've done.
Oh,
Is
is the evidence?
yeah, so admissibility, evidence, legal, charter.
Yeah, that's primary,
Yeah.
了解感觉，这个这个提升感觉，要搭配。
online. I get different angles.
Oh.
Yeah, I think all of them. This is like we accept that.
I think
We are, I checked it, yeah. It's live right now.
So, I mean,
Potentially. Yes.
I don't know. Yeah, yeah.
Well, yeah. If something is charges.
Yeah, yeah, that's the. So the I was, but I've really been involved for the last 2.5 years.
That's why I never.
I used to know. Okay.
Check 1, 2. Oh, there it goes.
Yeah.
Okay, can I have everyone's attention, please? So welcome, everyone. This is our first data science meetup back since the pandemic. So thanks for coming. I want to point out that we have some other kind of related meetups. So one is a data science reading group. It's really weird to hear my own voice. So that one is actually happening tomorrow and then every 2 weeks on Wednesdays. That one is still entirely online, but might be in person soonish. There's also a on hiatus meetup for table competitions, which hopefully will start up soonish as well. So keep an eye on our meetup page for both of those. Before I introduce the speaker, is there someone from Northeastern who wanted to speak about anything? No? Okay, I wasn't sure. But many thanks to our host here at Northeastern who's given us this space to use for free. So it's a lovely space, and please, if some of the students are here, please engage with them and help them find jobs and things like that. Okay, so our speaker, sorry? Okay, yeah, not that one. Some of them are off limits already. Okay, our speaker today is Justin Long, who is a public cloud specialist at Intel, which I think means he works with Intel users, helping them find solutions on the public cloud. So he has nearly 2-decade career in software with many artificial intelligence, machine learning, and distributed computing projects, a couple of which I found on his resume. So he had a project trying to automate online dating, and he's also worked with Skylines, so they're the makers of deep learning 4J. And in his spare time, he also works as a renewable energy investor and amateur photographer. Yeah. And if there's anything else, I'll turn it over to him for the talk. Thank you.
So yeah, I'm hearing my own voice too. When you hear your own voice, do you ever kind of focus on that nasally part of your voice? And you're just kind of, oh, you want to make the voice deeper. So you're actually getting a stand-up routine tonight? So I work a lot, I'm a public cloud specialist, and sometimes call myself a technologist. The reason for that is I work a lot with our end users, and the team I'm on works with a lot of our main big accounts. So, we're kind of planning hardware that's going in the data centers, but on top of that, we're doing a lot of software optimization as well. So, in addition to my ordinary job at Intel, I took on what I call grassroots developer relations, because there's so much technology in Intel that we're just not talking about, and that's the whole reason why I'm here today, because I think, from a machine learning perspective, addition stuff, and what you're working on might be interesting to you, but not just from a, Intel sales perspective, but also from, hey, there's a lot of interesting research and academic stuff going on. So today, I'm going to talk about neuromorphic computing and what that means, and how it ties into spiking neural networks. And then we'll end with another presentation, which will be short and sweet, on some machine learning hardware that you can actually use on AWS right now. That's brand new. So this is my first time giving this presentation. This comes out of the Intel lab. It's the Neuromorphic Computing lab, and it's the main guy behind this, his name is Mike Davies. I'll send it out through Dan, links on presentation to dig deeper into all of this materials. So if there's any questions I can't answer today, odds are there's a lot more material that's technical that you can dig into. This will just be kind of a nice introduction. So before we get started, in traditional Intel kind of legacy, I just want to be clear, any performance claims that we give today, there's kind of a legal disclaimer that comes with them, it's because Intel's been around for a long time. When you make chips and CPUs, you have to qualify all those claims. So just want to make sure that you're aware of the legal disclaimer. So let's talk a bit about what the current focus is of the Neuromorphic Computing lab. So right now, we're thinking about, we're especially thinking about kind of vision problems, and how does it tie into hardware. I'd say the best way to explain what the Neuromorphic lab is doing is trying to recreate the bird brain. And in neurology and neuroscience, over the last 10 years, our understanding of how the brain works is increased by what's happening. We're really starting to understand what the math behind neurons. And what the Neuromorphic lab is doing is taking that bird brain idea and turning it into actual software and hardware. So a lot of this is still in research. However, and I'll repeat this at the end of the presentation, we can talk about this offline, is if you're a practitioner who's especially involved in something like autonomous driving or robotics, we do have an industry program for chips coming out of the lab. So if you're focused on anything that's like robotics, autonomous driving, we do partner with the industry to take some of these chips and actually test them for real world problems. So, that's for anybody who working on something like a sanctuary AI. Is anyone here familiar with some of the local robotics companies and whatnot? I'm seeing some headlines. So that's really who's going to benefit from some of these neuromorphic chips. So developing the Neuromorphic lab is developing computing technology inspired by the bird brain. It's to really integrate this into computing products. So think about, edge. So actually, here's a quick question for the audience. What does edge mean to you when you're thinking of edge computing? So we'll come in front. Sensor-related data processing, yes, that can be edge computing. I think you can also think of like a Tesla car as an example as an edge computer because it's on the road, it's not connected, you don't need people going into it. That's really where a lot of these chips are going to have more benefit. So let's talk about the human brain. The brain is a fascinating place to do research because brains are not deterministic. Brains are probabilistic. And, the way that we've designed hardware so far has been very deterministic. It's the same way that we design machine learning models. So, there's a lot of currents, feedback loops, what kind of stays in the middle of the types of computing problems that we're solving that are, not so deterministic, but not so probabilistic. But really, to achieve brain-like computing, we're talking about self-organized growth. Think about when a baby is born. That baby is learning things in their environment, and their brain is growing and organizing. That's self-organized growth. Those neurons in the baby's brain are taking in sensory inputs, and they're developing their own neural networks that are constantly changing. The way that we do deep learning today, in a very simplified way, I like to say it's kind of like a waterfall. Everything's just kind of falling at the same time. It's very synchronous. It's very deterministic. So how do you take something that's probabilistic that is not synchronous and take that into hardware. So this is where the researchers came and said, okay, well, we need to solve for algorithms and hardware that work together. So, you know, to kind of look at if you look at the middle bottom of this slide, initial neural networks, again, they're like that waterfall. Well, neuromorphic networks are constantly changing. They're event-driven, they're temporal, everything is event-based, and they're sparse. If you're, you know, let's say you've trained, well, actually, who here is working specifically with deep learning? Raise your hand. I see one hand. So are the rest of you running like XGBoost, or what kind of machine learning problems are you working on that's not deep learning? Or models, we'll say, or algorithms? Somebody speak up. I'll let you respond. Okay, so you're doing XGBoost. Okay. Okay, so I guess for the purposes of this, I'll kind of keep it constrained neural networks. But you know, again, like I think XGBoost, when you're working with like random forests or any kind of you know, adding gradient boosting on top of that, you know, still very deterministic. You're training a model, you're doing you know, you're having an input, you get synchronous output. You know, there's kind of a fundamental very static in a sense, right? It's not flexible. Like let's say you train a neural network. You know, certain nodes in that network are kind of be more relevant than others, right? But still, when you feed an input in that neural network, it's going to go to that whole network. There's software out there to kind of trim those nodes and just shrink the size of your neural network, but that's still what's happening. So we need to start mimicking in our hardware these new novel neural-inspired algorithms. So our silicon, the silicon that we're making, the chips, needs to rely on temporal neuron models. It needs to have an asynchronous design. You need to have digital circuits, not analog circuits. And you need to support plasticity. Who knows what plasticity means? Raise your hand. Tell me.
What do you mean?
Yes.
Plasticity is the ability of the neurons to change and adapt.
So plasticity is the ability of the neurons to change and adapt. That's a really good response. And that's exactly where we need to go with the hardware. The hardware needs to enable that. Are you using spiking neural networks already?
I'm reading.
You're reading? Okay. Did you do your homework before you came?
Not as much as I should have.
That's fine. So let's look at the conventional solution. So we're taking featured encodings. We're going to run a compute operation on them. There's much more activity going on here, and it's requiring higher energy. You know, sometimes the matrices that we're inputting in compute, you know, they can be huge, right? And often what we'll do is we'll iterate through all the features. So this can be very power intensive. So when you're thinking about edge computing, and you're thinking about, well, what is in a car? You know, there's implications, right? You're gonna have attacks. Now a car, you know, let's say you're driving Model 3, you probably have something like 72 kilowatt-hour battery in your car. That's a lot of power. So you'll be able to do some of the autonomous driving that is running in those GPUs in that car, ASICs, and what it is. But what if it's a drone? Well, you're not going to have 72 kilowatt-hour battery in your drone. You're going to have a lot less power. And your drone's going to only have a limited flight time. Maybe you can go 7 kilometers and back, and that's it. So you run into power limitations, and you really have to think differently about hardware. So you have faster operation, but you don't have a faster result. Higher activity consumes more energy, and communication is a bottleneck. let's look at a simplified example where we're going with this. Kind of like a spiky neural network. So you're going to start, let's say you have 10,000 neurons. You have standard binary encoding, but it's very expensive to send so many neurons. Well, you can use sparse temporal encoding. Who here is familiar with ND arrays and works a lot of scientific computing arrays? Quite, like what about NumPy and, how many NumPy users here? Yeah, NumPy. Sorry, I think it is NumPy. It's Python. It's like a meme out there about that, I'm sure. So sparse matrices are a lot more performant than dense matrices. But as someone who worked on a deep learning framework, I can tell you it's to implement sparse matrices. It's a challenge. It's really a software and implementation challenge. But when it comes to performance, when you think of neural networks and performance, there's real gain. So sparse temporal encodings. So now what we're going to do is we're going to feed these sparse encodings. And right now this example is just showing you one neuron's temporal signature. Oh, it's a match. And you might say, oh, it's a cat. That was a sparse match, right? The rest of the network is also pivoting this. So, the rest of the network is saying, oh, there's no matches here. I don't need to perform this computation. So, some of them might fire because it's a weaker match. But you still know which one's stronger. But as a whole, when it comes to this quote-unquote spiking neural network, kind of this simplified example, you're saving power. And that's really important when you start to think about edge computing, edge devices, something like that. So, traditional deep learning relies on stateless neurons. And you can, like I described before, it's like a waterfall of calculations and everything's just getting fed through at the same time. But spiking neuron is going to be a little different. They're asynchronous, and they're going to have non-linear filters. So they're sparse and they're event-based. So again, think about how this is going to have an implication on learning. Sparse communication and asynchronous communication is fast and efficient. Your result is going to come. You're not going to have to feed all those matrices through. Inside the network itself, you're going to have intercommunication. So you don't have to worry about all this attached from the power required for that. So this is going to lead us to a new class of computing architecture. So we started with standard computing. So this is kind of your programming by encoding algorithms, synchronous clocking, sequential threads of control. So we're going to move to, after that came parallel computing. So offline training using labeled dataset, sets, synchronous clocking, with parallel dense compute. And then we have neuromorphic computing. So taking those spiking neurons, sparse, asynchronous communication, we're going to learn on the fly because each neuron is going to be firing its own rules. We're going to have asynchronous event-based spikes, and we're going to parallel sparse compute. Let's introduce the chip that's responsible for all this. So Intel Labs developed Loihi. This is a neuromorphic chip meant specifically for spiking neural networks. So the key properties of this chip are compute and memory integrated, and this is to spatially embody program networks. So it means that the hardware is mimicking how the neurons are firing. You're going to be able to use temporal neuron models to exploit temporal correlation. It's really important for something like vision tracking. Spike-based communication to exploit temporal sparsity. So, not everything is getting fed through at the same time. Sparse connectivity for efficient data flow and scalability. On-chip learning without weight movement or data storage. and digital asynchronous implementation for power efficiency, scalability, and fast prototyping. So you don't have floating point numbers yet. There's no multiply accumulators, and there's no option DRAM, which is kind of fundamental to deep learning hardware. Limitation. So what is chip implementation with asynchronous design? So this was commercially developed over where the Luigi, or the precursors to the Luigi came from. It came from Fulcrum Microsystems, and it was over about 15 years. It was applied to 5 generations of commercial Ethernet switches. And the power consumption scales with activity, which matched really well to spiking neurons and sparse interconnectivity. This allows a neuromorphic mesh to operate about 1,000 times faster than biological speed using emergent synchronization, and it supports low energy, highly ported SRAM orbits. That was a lot of hardware speed, and I apologize for that. I know everyone here is data scientists or using some kind of machine learning, but there's a whole, we'll call it rocket science, the actual chips and where it's coming from now. So Luigi itself, there's been some precursors to Luigi, but Luigi itself is really proving its value with spiky neural networks and the design of this chip. And some examples of where it really applies is something like gesture recognition, odor recognition, combinatorial optimization, and seeing understanding of robotics. I think for most of you, who maybe what your current problem solving is actually not most of you, but I think robotics are probably going to be a big one. But just the different types of learning that you can do. So learning with synaptic plasticity. So as we described it, go ahead.
Question on the previous side, said that it's 50% faster versus the GPU, right?
Yes, and I'll explain that in a second. It depends on your problem that you're solving and the complexity.
That would be a significant improvement. GPUs are already very good for the network.
Yes.
The question.
Okay, so the question was, so this slide says it's 50% faster versus the GPU, and that's specifically for adaptive robotic arm control. And it's not a blanket statement; it applies to that problem set, and you'll see why in a second. It has to do with the complexity of the problem.
50% improvement, is it just for inference, or do you get 50% lower gain?
So that would be for training time. And again, I'll show you here in a second. You'll actually see, I'll have a graph here I'll show you in a second, and we'll show you the different problems and how they're kind of laid out. So I think we already covered synaptic plasticity earlier, but in neuroscience, synaptic plasticity is the ability of synapses to strengthen or weaken over time in response to increases or decreases in their activity. And what that basically means is, so let's say you have a neural network focused on vision. Well, let's say that neural network is driving your car. Let's say it's controlling the steering wheel. It's probably going to start not use the neurons that are related to tracking an airplane in the sky, because for 99.999% of the time, you don't really need to worry about that airplane unless it's making an emergency landing on your highway. It does happen. But, not something that's important. And what plasticity gives you is the ability to not focus on, quote unquote, activating those features or focusing on that. Instead, when you're steering the car, you want to be more focused on things that you're always seeing on pedestrians. So, where this is going on the software side is you want the car to be better over time as it gets more driven. So Luigi, the chip, demonstrates value when the workload increases in complexity, especially when order is magnitude. And especially when the problem is temporal or event-based. So it provides extremely good scaling versus conventional architectures that emphasize growth. So standard feed-forward neural networks, kind of like just the basic multi-layer perceptron, it's going to give you the least compelling gains on the lead. You might as well just use the CPU in some cases. Like there's a lot of, at Intel, what we've been doing is all of the Xeon CPUs are going in cloud instances now. We've been adding a lot of accelerators for, vectorization, specifically for deep learning. So you can just do inference on cloud CPU. You don't have to deploy GPUs. Let's say you're deploying on Amazon. You can deploy, inference for standard feed-forward neural network just on an N6i, and you'll get really good performance. So you don't have to use GPUs. But let's say we get complex problems, especially that have IO-inspired properties. This is where you start to see the best gains, and it really is orders of magnitude. So, graph search, really good one, where graphs can be quite complex in their nature to solve as of the calculations that are happening. Luigi excels in this. It excels in actually I'll put a slide on kind of gets deeper into it, but kind of in straight, you're solving for constraints. So let's say you have to do the traveling salesman in the shortest path. Well, what if you have to have a constraint attached to that? That's lasso, that's Luigi, Excel problem that they can solve. So let's zoom in on some of these examples. So I talked already a bit about traveling salesmen. So we'll call that graph search. This is the shortest path. Constraint satisfaction. So taking the shortest path and adding. Let's say you have to visit each waypoint once. Optimization problems. This is where Luigi is really going to excel. And you can see, some of these, you can see where it's really going to also apply to recurrent networks and where this can be expanded temporally. So this is where you can have a great chip. Luigi's going to inspire chips for things like drones and really adding autonomy to cars and robotics. So let's look at a key insight here. So neuromorphic networks efficiently optimize solutions via stochastic gradient descent. So spiking neural dynamics corresponds to an approximate gradient descent of the energy function, and therefore minimizes the number of constraint violations. So as a spiking neural network performs stochastic state transitions, energy is reduced on average. So yet occasionally the network may get trapped to local minima, which is normally a problem for similar energy-based solvers. This is kind of just showing you where you're escaping that Okay, so how does Luigi perform? So it outperforms leading optimization solvers by orders of magnitude. So since Luigi has been benchmarked on other problems in the algorithm process, one of them is using QO. I did the example of solving an MIS problem which would find gains of up to 4 orders of magnitude in EDP. So MIS is a generic NP-hard graph problem used, for instance, in computing biology. And QO is especially interesting because it's a generic algorithm that has been in the workhorse algorithm. It's the workhorse algorithm high current quantum annealing approaches, which other companies are also building special purpose accelerators. So it's comparable. Solving hard constraint optimization problems is an interesting application because such problems are ubiquitous in the real world in virtually every industry. A particular interesting strength application is when you combine AI and optimization problems during real-time perception. So inferencing or planning tasks or alternative optimal courses of action must be decided economically. So you can find these problems in robotics. Sorry about that. And read through my notes. So you can find these problems in robotics. And this is just an example of what we can apply to model predictive control. So what's happening in this example is your model predictive control will refer to as MPC. You're going through every iteration of the MPC. And what's happening is, your robot needs to figure out your obstacles, your poses, needs to figure out obstacle avoidance, and maybe it's gate. So that one there is, I think that's the Boston Dynamics robot. Does anyone recognize it? So what's happening is, when you're going through all these iterations, you have a computationally intense solver that can be accelerated with the wiki. So let's talk about how to program for this using tracking networks, so dynamic neural fields. Anyone heard of dynamic neural fields? So that's going to be new to everybody. How are you all feeling so far? I know it's a lot of dense material, so I just want to make sure it's still interesting to all of you. Okay, good. It's really, I'll be honest, it's really research heavy. Okay, so a lot of this is still the academic side, and one of the biggest focuses right now coming out of the lab is taking this to a more consumable application. So getting it integrated in the frameworks, getting pieces of software that are more composable out there. I think that's one challenge is when you're dealing with research material, it's going to be very new, and it's sometimes it can be very dense. So I appreciate you guys hanging in there. So dynamic neural fields. They're neural attractor networks that generate stabilized activity patterns in recurrently connected populations of neurons. So these patterns form the basis of neural representations, decision-making, working memory, and learning. And it's the fundamental building block of dynamic field theory, which is a mathematical and conceptual framework for modeling cognitive processes that encode behavioral movement. So again, we're getting closer to the human brain. We're trying to take neural networks and getting them to act more like the human brain. Here's a perfect example. So object tracking with dynamic neural fields. So what you're seeing is in that middle image is you're seeing the voltage, a selective dynamic neural field tracking moving input. And you can even see it at the very far right when you track something without DNS, or when you track with it, there's more of a temporal connection. So if you're already tracking one fish, you're going to keep following that fish. But the problem is with conventional networks and conventional techniques, well, multiple fish are moving. You might actually jump from one fish to the other, and you don't get accurate object tracking. And this is really important, say, for autonomous driving, because when you're trying to track a pedestrian, you want to get a really good idea of the trajectory of that pedestrian. So if that pedestrian is, let's say there's 5 pedestrians, but you're tracking all 5, but you're all kind of going in different directions. Well, if your tracking is jumping from one pedestrian to another, you're going you're gonna get a poor trajectory of where the pedestrian is going, and you might run into them because, oh, wait a minute, my calculation was off, all of a sudden I start tracking a different pedestrian, and I just ran into the pedestrian that actually mattered. So that's something that's really important with, let's say, like object tracking. And this is why dynamic neural fields are really important with like Luigi, for example, moving forward. So we're going into a new era of neuromorphic computing. So we have proven computational value. We're motivating a new computational paradigm. And remember, we're going from deterministic to probabilistic. And there's a lot of successful learning algorithms. Not a lot. Well, sorry, I should say they're very shallow, at least according to this slide. But it's developing, right? And again, like the certain problems that we're trying to solve, like especially with something like autonomous driving, it's going to have a huge impact. So where do we want to focus these applications? So if you have power constraints, if you need low latency, and you're working with real-time signals, that's where it's going to be important. I think power one is especially, as I've said over and over, hey, you can stick a GPU on a car, but you can't stick a GPU on a drone. You're just not going to have the available power for that. And you need something that has slowly evolving structure. So, think about my example earlier where you want to get better at learning how to track pedestrians. You don't really need to be better at learning about tracking the airplanes and the seagulls in the sky. So where's the commercial value? Well, this is basically the path to commercial value. Right now it's still in the lab. So unless you're, highly specialized robotics company, we have programs for you to take chips from our lab and work with you. But really we're not in the prime time yet. So we're looking at specialized designs. We're looking at how to take that into a form factor that works at the edge. And we're also looking at how to scale this up in the data center. What are the problems with that? Well, it could be a high cost due to on-chip memory integration. So when you're integrating memory onto the chip, there is cost to that. And that's where you'll see that in the application side. The algorithms and the programming models are still, again, in the research phase. And there's software convergence. So what the software convergence means is, if you download PyTorch or TensorFlow, it's going to be ready to go out of the box. And do PyTorch and TensorFlow agree on what neuromorphic and spiking neural networks mean to each other? That's where the challenge is. So right now, I introduced Luigi. So Intel has moved on to Luigi 2. So there's a whole new iteration of Luigi that performs even better. And it comes in different form factors. So Luigi 2, cabinet for a data center, and then there's stackable H-chip board, and there's a great image you can see in a few slides. It's an H-chip board that some of these chips fit in the size of your finger. It uses a 4 nanometer manufacturing process. Oh, and Lava, right? And that's a software framework, which I'll get to in a second. So what's the difference between Luigi 1 and Luigi 2? Well, Luigi 1 and 2 never hit the market, but we're going to be excited about the performance improvements anyways. It's 10 times faster. You can handle 8 times more neurons, and it has better scaling and integration. For example, when you're taking kind of that H-chip board and you want to stack those chips, you'll be able to scale that out a little better. It has a generalized and optimized neuromorphic core, and we'll get into the details, but when you're thinking about generalizing hardware, what you want to think about is, okay, well, how do I take this chip architecture and make it work on a bunch of different form factors? And then how do I generalize it for, program the software so spiking neural networks. So, moving out from not just an ASIC, it can be used for more than just more different types of computation. That's really important. And I think these are just some selected measurements that I just wanted to share with you. But this is the most interesting part. So remember I was talking about the drone and fitting, we need to use low power and we need to fit this onto edge computing devices that are really small. So this one, this global point is a stackable H chip board. The chip fits in the tip of your finger. So you can see the size of this. You can see just how small this is. And that's really important for low power edge devices, autonomous drones, where power and weight mean everything. So that's where it becomes, this is where it's fundamentally changing beyond the GPU. So the other thing that you can do with the new OBT2 is you can do resonating prior neurons. So conventional deep neural networks provide a powerful example from which we can begin to explore architectures and algorithms for spiking neural networks. But the potential becomes even greater when we can exploit the unique properties of spiking neurons. So as an example, we might highlight the resonating fire neurons, which have an oscillatory internal state with decaying magnitude. And Mike Davies in the lab did a recent paper to show, it was based to show how a network of resonating fire neurons can perform tasks such as estimating optimal flow from the string. If you guys are interested, I can link you to that later. But it's, it's optimizing more what you can do with spiking neural networks. And, you're able to solve harder problems. That's really the gist. Here's the great one. So remember I've been talking about driving power and autonomous driving. So OBT2 in the lab has been deployed for autonomous driving, and specifically to become better at vehicle control. So the big thing that I think is that will highlight when it comes to OBT2 is the mean square error is 32% lower. You have 5 times less neuron cores, so you're doing more with less. And it's about 9 to 12 times faster, so you have more throughput. So this in terms of frames per second, you're running about, I want to verify this, but it's about 7,000 frames per second, which is pretty damn fast. That's all frames per second. Now, I think if you look at some of the cascading neural networks out there, for any of you who are doing like vision, they're achieving, like on GPUs, they're kind of achieving like 60 frames per second. So this is really significant in terms of the performance you can do. Now, I'm pretty sure that's with the scaled down resolution. But it's really just to show you, hey, like this is game changing. So what software are you going to use? So let's say you're a researcher, and what software are you going to use with Wiki today? So Intel Labs built a framework called Lava, and it's specifically for neuromorphic computing. By the way, is anybody here a researcher? So we're all kind of practitioners, software engineers. Is that kind of just the audience? Okay. So I won't go too deep into Lava because I'll be honest, it's entirely research focused. But the advantage of this over using something like a TensorFlow or PyTorch is you're going to have multi-platform support, you're going to have hardware acceleration, but you're also going to have, spiking neural networks as well as the open source licensing that come with that. So as you can see across the board, a lot of different frameworks come with this, and some of them are purpose-built. But Lava is really meant to cover all of the above. And it's really for researchers, to be honest. Multi-paradigm, so you can do optimization, you can do neural attractors, you can do deep learning, and you can do vector symbolism. So Lava you know, you can use it in different flavors, and it's primarily for researchers, I would argue, unless you're solving some really complex robotics problems. But I don't see this being used out of the lab in the next year or two. I think it's really going to be, when we talk about software convergence and when all those features are getting into, say, PyTorch, that's when, you know, we'll be able to market and scale up, you know, a lot of the applications kind of open and accessible to everybody. Here's where a lot of it is kind of interesting, especially if you're, you know, from a research point of view, or if you just want to experiment a bit with the research. It's multi-platform, so that means that you can prototype this on CPU. So you don't just have to try to get access to a wiki chip. You can prototype this on CPU and you can simulate it. And I think that's what's most important because, you know, it's, again, how do you access this? How do you get accessibility to this? So that's the, I know that was pretty dense material. That's everything on neuromorphic computing. This is just a kind of a summary of all of our performance analysis details. But if any of you are interested, so Lava is on GitHub. It's just github.com/LavaNC. And you can also email the lab if you want more information, or you can just reach out to me. If you got something like a robotics program, I'm really happy to connect you with the lab because we partner with industry to test some of our products on the lab. So that's the comment. So with respect to where we're going with this, so neuromorphic computing, again, still a research, right? It's still in research. It's not yet ready for prime time, so right now, partnering with industry to test and figure out how we're going to market this. So really, what do you want to do today? So who here is training machine learning models with multiple GPUs? So who here in the audience, raise your hand if you're training. So I see one hand, two. What's that, sorry? Okay. So you, sir, how many GPUs are you deploying your models on for training? 6. 3 to 6. Okay, so that's significant. Are you doing that in the cloud or are you doing that on a workstation? Okay, so it's a workstation. And just out of curiosity, you know, in terms of when you're doing that training, using like sandblast, like in terms of, how are you synchronizing your gradients? That's what I meant to say. Are you sharing your gradients as well? Okay, so you're letting PyTorch handle all of it. Yeah. And then what kind of acceleration are you getting? So you're training time from GPUs to multiple GPUs. Can you give me an example? Got it. Okay. So memory, batch size, those are all your constraints, and that's the reason why you're scaling out your GPUs. So some of these models, so this could very well apply to you, and for anyone else who, let's say you're scaling out your training. So let's say you have like a vision problem that you're trying to solve, you're developing a vision model. I think that's especially where multi-GPU training starts to become interesting. So I want to talk about Intel bought a company called Bonna, paid $2 billion for it. And Bonna is really special because they focus on ASICs deep learning. So I'll quickly introduce you guys to Gaudi and Gaudi 2. I think that actually would have been correct over this one, but it's in there in the title. And you'll get to see kind of where if you're focused on performance optimization and cost optimization, which depending on the size and scale of machine learning training that you're doing, this will be really relevant for you. And for anyone who, let's say you go to work with Twitter someday, and you start working on really large NLP models, you know, this will be something you want in your back pocket because you'll want to say, oh, wait a minute, I gotta deploy on, let's say 50 machines. I know exactly how to optimize that cost. So today, for all the big companies out there, Intel sees the data center accelerator market, growing significantly by at least 36%. And it's really deep learning driving growth because more companies are deploying deep learning in production. And a third of the servers, or our prediction is a third of the servers that are going to be shipped in 4 years are going to run deep learning training records. So it's going to account for the majority of the cloud workloads. And I think you see this again in really large companies, for what you'll see, say, a social media company do when they're building kind of a vision model or an NLP model. It has so much data. They'll run this on 1,000 machines. If they want to train a new model, they'll run this on 1,000 machines. It's happened before. I mean, Tesla built the whole data center to train their models for autonomous driving. So I know that for most of you in the room, you're not really focused on problems at the scale, but when you have that much data, you'll find that companies that big consume a lot of the machines at at AWS doing training on their models. It's actually quite incredible the spend that happens through that. So what's today's cost to train? The cost to train is the biggest barrier to AI implementation. So when we did a little survey, 56% of the respondents said, well, the reason why I'm not scaling up my training is because of cost. And it's especially because if you're trying to run GPUs on AWS, it can be a pretty penny. So that's why we introduced Counting. So it's a purpose-built ASIC, and it's all for training efficiency and for scaling up that training. And this is designed to optimize AI performance. You're delivering higher efficiency than traditional CPUs and GPUs. So we want to retrofit kind of that whole training process that folks are doing across these hundreds of thousands of machines to address these AI training needs. So this really isn't about trying to leapfrog GPUs out there. It's about making them more efficient. And that's why it's easy. So what you can do today, so we have training instances available or machine instances available on AWS. So let's say you want to do some scaled up training. You have a model that you want to train today. You can go on EC2. We have a few availability zones that are running these machines. One of them being Oregon US West 2P. I know that's specific. And you'll get 40. What's that? There's also, I think, some in Virginia, and there's another zone that I don't remember at the moment.
Right, but specifically the zone, not the region.
Yes, yeah, these just got deployed. They were just deployed. And we do have some companies using them already, but the whole advantage to this is, you're getting about a 40% better price performance than the latest GPUs that you might deploy on AWS. So, again, this is all about cost efficiency. So I think what your job title would be is, if you're running this, is you might be a machine learning engineer, not a data scientist. So you're someone who's taking that work from the data scientist, you're deploying it in production, and you're saying, oh, wait a minute, we have petabytes of data, we need to scale out the training to many machines. We need to save money on this. So we would use DL1 instance to scale that out. And this is how companies are doing it today. I think, that machine learning engineer job title, it can be different depending on the size of your company, but at a larger company, machine learning engineer is taking that deployment from the data scientist and they're figuring out how to scale that out. So what does that performance look like? So when you compare it to, we're going to compare it to A100s, we're going to be in the middle between the A100s and the B100s. But we're going to be faster than the A100s. We're going to be more cost effective. And that's with vision. And significantly faster than A100s when it comes to NLP model training. With the BERT phase 2 pre-training, not the phase 1, but the phase 2. But the cost savings are significant. So when you're looking at, ResNet, for example, compared to, V100, you've got about 77% cost savings there. So it's very significant. So if you're thinking, oh wait a minute, I need to scale out my machine learning training, I need to deploy 100 machines. Well, okay, well V100s are brand new, they're fancy and everything, but they're not going to be in my budget. Well, again, this is what ASICs are about. This is the problem that we're trying to solve. It's really about cost performance. And so you just do more training. You do more training with less budget. So Gaudi 1s are in the data center today. We just developed and we're right now releasing Gaudi 2. And this is probably more something you'll see in a lot more of those, hyperscale machine instances that are going out in the cloud. But Gaudi 2 is really special for a few reasons, but I'll get to that in a second. So with a huge leap in process node, you're going from a 16 nanometer manufacturing process to 7 nanometer. Intel said, okay, well, let's take the efficient architecture and pack a performance boost into it. So the NVMe and the TPC compute clusters are going to be much more powerful. And instead of 8 TPCs, we're going to have 24 TPCs that we're upgrading internally with additional functions. And on top of that, we're going to utilize the memory more efficiently. So you're getting an ASIC specialized for deep learning that's going to be much more performant. So here's the difference between Gaudi 1 and Gaudi 2. So for ResNet, it's a 3x performance boost. And for BERT, large BERT, it's almost a 5x, So this is, you're going to see more of the Gaudi 2s in the future in the data center. We have limited DL1 instances. This is really where we're going for more scaled out deep learning instance training in the cloud. And you can also use it on-prem. So if you have your own data center, let's say you want to build the equivalent of Tesla's supercomputer that they put together for the autonomous driving, you might want to pull that with Gaudi 2. It's the same. So we have an array of architectural advances, which I described in the previous slide. But your total cost of ownership, your increased TPCs are going from 10 to 24, and your on-chip memory is going from 32 to 96 gigabytes. So I think the gentleman in the front who mentioned that memory was one of the constraints, and the reason why you're scaling up to multiple GPUs, well, we're just packing more memory into these ASICs. And here's why it's special. So Gaudi 2 outperformed NVIDIA's A100 on ResNet and BERT. So this was kind of really important in Intel because finally Intel had bested NVIDIA at the AI performance problem, at least for now. So it's probably going to be short-lived, but we're going to ride it as long as we can. And then remember how I was saying with Loihi how software is really important, and you need that convergence of software. So if you want to deploy with the Gaudi instances today, PyTorch and TensorFlow are going to already work with that out of the box. So you'll be able to train deep learning on Gaudi with minimal code changes, and you're going to have already a library of performance optimized kernels available to you. So let's say you want to go on AWS right now and deploy a DL1 instance. It's pretty simple. All you have to do is just select DL1. There's, I believe, a quick start AMI that runs on Ubuntu, and it has the Synapse AI, and I think it might have Jupyter too. Don't hold me to that. Otherwise, we'll make one. And you can deploy it right off the bat. I will warn you, if you run it for 2 days, it'll cost you $650. So make sure you're using the company credit card on that one. But you know, I think about, again, when you're a company that's deploying deep learning at scale, and you're using hundreds of machines to train those models, then that $650 could have been, you know, over $1,000, and all those numbers are going to add up. Ultimately, it means more machines you can deploy and faster you can train your models. So we did publish the results online, and I'll share all these slides with you if you want to see kind of the comparison to County and what NVIDIA is doing right now. But I think when we talk about machine learning hardware in the lab and what you can do today, well, today is all about, you know, efficiency improvements, getting cost improvements, and then tomorrow you'll see all those energy improvements, spiking neural networks. That's where it's going tomorrow. But if you want to get involved with today, I mean, this is where at least Intel is going with it. That's the end of the show. So are there any questions? Yes, go ahead.
I have a question about the first part of the presentation, very valuable. So with that, is there a software like paradigm change, like you write different rule lines for that to optimize, or is it the same structure you think better with more energy efficient? Does it get better with the current way of doing it?
So your question is there a paradigm change in how you write software for neuromorphic computing versus conventional deep learning? Well, when it comes to the Wiki chip, the simplified answer is going to be both. It depends on what problem you're solving. So as you saw in some of those results earlier, you know, Intel is running Resonant 15 on the Wiki. And, you know, in terms of kind of like graph solving problems, we can run that on the Wiki with some performance improvements. So those are things that you can write with traditional software in the same software paradigm. But if you want to get into more complex problem solving, you're changing the paradigm. And you're going to be writing neural networks a little bit differently. So if you want to get into better object tracking, for example, if you're doing autonomous driving, you're changing the paradigm. And I think right now, I'm not too familiar, like for example, I'm not familiar with how Tesla trains each one of their models, but I believe that what Tesla does is still very deterministic. And I think what they're doing is, you know, they're kind of cascading their neural networks together, feeding into different things with the car, right? But where it's going is, you know, you won't have it, you'll have more plasticity, you know, kind of like how when the child, you know, we talk about the baby kind of learning things in their environment, how their brain grows and forms new neural connections. That's where we're going with neural networks, and that's really how it's going to change everything. But yes, it'll require to solve those kind of problems, those really complex problems, you'll have a different paradigm. Yes. This one? So first question for you, was this the table you were referring to? Oh,
The other slide deck.
oh, was it the other slide deck? Let me see if I can find it, 'cause I just want to see, so it was early on in the presentation. This one? Actually. Yeah. You know, that's probably a question for Mike Davies. So what I would recommend is, I can get your question by email, and I'll take that question to Mike, and then I'll have it sent out to the group. Because he'll be the one best qualified to answer that. So you're referring, I think I know which one you're referring to. You're talking about the CPU when it comes to Lava. So that refers to the software side, so the software framework called Lava. I don't think it might integrate with TPUs. That might be that, you know, at the bottom of the list here on the bottom right, it says others. I personally have not heard of Lava working with TPUs, but I know that, so our question to you is, are you deploying your models in the cloud on GCP on TPUs? You are. And how is that through, you're not deploying TPU instances, but you're deploying it through an API, is that correct? I doubt that Log is going to work with it because I think the way that GCP is set up, when you want to deploy models, it's really all through APIs. I mean, this is a little more like on-prem, hands-on based, where Log is really meant for the research side. I don't think they would have integrated it with TPUs. I can check, I'll check. Just out of curiosity, is there a problem that you want to experiment with on Lava? So you're saying the TPUs, yeah. So TPUs, because I think TPUs are also an ASIC. It improves efficiency as well. I would personally respond to that with an Intel bias to say we should try our galleys. Any other questions? Go ahead.
Question. Do you have any idea how this goes in the API? It doesn't feel like speed and efficiency is something.
That's a great question. No, that's a great question. I do not know where the name came from. I think Kavana came from Israel. Let me double check that. I believe they were based in Israel, and that could, maybe it's from Israel. I'll look into it. There were a couple of acquisitions we made, and I might be thinking of the wrong one. I might not be from Israel, so. Yeah. So Intel's made a few acquisitions recently, and all related to data centers. I know one of them is in Israel. I want to say it was Lana, but it might actually be Granulate. I'll double check that. We're going to be confusing my acquisitions. Any other questions? Well, it's 7:40. I guess we need, an hour, 10 minutes. So I'll let you have the rest of your day back. we have a reservation across the street at Library Square, correct?
Yeah.
So for those of you who want to just kind of come, socialize and chat after the meetup, we have a reservation for a table over at Library Square. So you're welcome to come, have a drink of your choice, and just socialize. But I really want to thank you guys for coming out. I know this was a very hardware-centric presentation, but I think it's important, you know, it's, everything machine learning is a GPU. There's a lot happening out there that's in the lab and emerging in the data center, so it's fun for me to share. So I really appreciate your time today.
A good question. Has anyone been to a meetup in the past 2 years? My first.
That's going to be the same for me. I have not been to a meetup in the last 2 years. Yeah. I didn't go to my first event, my first kind of large group event back in April. That was my first one where it was like, it was so weird because I was shaking hands, I was drinking with other people. You realize how antisocial we've been for the last 2 years. So this was actually really nice for everyone to come out and say hi and get to know all of you. So thank you. Okay. Did you want to say anything in terms of?
No, I would love for someone.
I think you just have power button.
Yeah, I might have to do that. But yeah, so thanks for coming, everybody.
I think we should also thank Northeastern University for their kind loan of space.
Yeah, so thanks to Northeastern University for the space. Thanks to everyone for coming. We hope to do this again in the future. So if anybody has anything they'd like to talk about, to be a speaker up here, please get in touch with me through the meetup group or through our Slack channel, which you can find through the meetup group. Aside from that, yeah, thanks for coming, and everybody is dismissed.
Yeah. I was still here that phrase.
So yeah.
Some people are going to Library Square.
So I'm so grateful. Yeah, but no, I don't until back.
End street, perfect.